Right now, the Milky Way is tearing apart smaller galaxies that got too close, leaving behind long, ghostly streams of stars. These streams don't just tell us where galaxies have been, but also show us what holds galaxies together. This is about galactic forensics, and we're about to dig in. In the 1970s, Donald Lyndon Bell spotted peculiar alignments with the globular clusters, dense regions up to 1 million stars orbiting the Milky Way. Several clusters lay along a line in the night sky, suggesting a shared origin. He wondered if they came from a shredded dwarf galaxy, but his forensic plates weren't deep enough to reveal the faint stars that would confirm his hunch. The idea remained an intriguing theory without proof. Everything changed in 1994. Rodrigo Ibata, Jerry Gilmore, and Mike Irwin pointed their telescopes to Sagittarius and saw something no one had seen before. A continuous ribbon of stars arcing around the galaxy more than once. They had found the Sagittarius Dwarf spheroidal galaxy in mid-disruption. Suddenly, galactic cannibalism wasn't a theory. It was unfolding before our eyes. Astrophysicists raced to reproduce this in simulations. They placed a dwarf galaxy in orbit around a Milky Way-like host. The host's gravity pulls on the dwarf galaxy, but the force that it exerts is unequal throughout. Some parts of the dwarf galaxy are nearer to the host than another, creating a stretching effect, where one side gets pulled faster than another. This causes the shape to be warped into streams of stars. Each close pass strips stars off the outskirts. Over successive orbits, the satellites lost mass. Its stars tracing two arms, one leading and one trailing along its path. They named this tidal stripping. But if we know exactly how those stars are moving today, we can rewind their paths and guess where it'd be in the past. Just like rewinding a footage of a shattered glass reforming, we can reconstruct the galaxy's past just by watching where the pieces flew, like forensic ballistics. We can find the residue of the mass and trace back to where it used to be using physics. Early searches based on star counts gave tantalizing hints, but no clear motion. That changed in 2013, when ESA's Gaia spacecraft launched and began its survey. Instead of just images, Gaia delivered a movie. It measured positions, parallaxes, and proper motions for over 1 billion stars with micro-arcsecond precision. In 2018, Gaia released its second data of what movements it saw in our galaxy. Astronomers looked and saw groups of stars moving together across the sky. They ran algorithms that looked for coherent streams. Suddenly, many more stellar streams jumped out of the data. GD1, Orphan, Jellum, and Helmny, the list kept growing. Could this be a fluke? Finding motion wasn't enough. Astronomers needed to be sure that these weren't just clusters moving together by chance. To truly confirm that, they turned to spectroscopy, detecting the cluster's chemical compositions. A group of stars sharing the same motion, distance, chemical composition, and age? That's a stream, born from a single progenitor. But these streams do more than just record galactic events. They're also uniquely sensitive to gravity. We know that dark matter makes up most of a galaxy's mass. We did a deep dive of it in a previous video if you don't know what it is. Anyways, dark matter makes up most of the galaxy, but cannot be detected using light, only gravitationally. The current main theory, called dark matter, assumes dark matter as particles that move slowly in groups together into small but dense subhalos around galaxies. Alternate models include warm dark matter, which smooths out small structures by having faster, lighter particles, reducing the number of subhalos. Self-interacting dark matter allows these particles to collide with itself, changing the shape and density of halos. When a subhalo of 10 to the 6 to 10 to the 8 solar masses fly through or near a stream, its gravity imparts an impulse, opening gaps and causes distortions. For example, in the Palomar 5 stream, we can see these gaps in predictable offsets. By comparing multiple streams, we test dark matter models. Streams really become gravitational seismographs, feeling clumps that are too small to detect traditionally by using light. But there's a major limitation with this approach. We're embedded within the system we're trying to map. It's like trying to reconstruct a spiral from the inside of a whirlpool. What happens if we flip the camera and look outward at other galaxies from a third-person perspective? In Andromeda, several massive clean streams arc across its halo, some over 100 kiloparsecs long. Their orbits and wrapping patterns suggest multiple infall events. One stream, for instance, shows shell-like folds consistent with a nearby radial orbit. These shells form when the debris slows near the apocenter, piling up and creating surface brightness enhancements, directly observable from our vantage point. But here's the core. Many of these streams remain surprisingly thin and unperturbed, despite Andromeda's mass being comparable to the Milky Way's. That challenges what cold dark matter predicts. If subhalos are everywhere and dense, they should have stirred these streams, heating them, creating gaps or traverse displacements over gigayear timescales. But that's not what we see. So what are their possible explanations? 1. Andromeda's halo may be moving more orderly, or its subhalo numbers are less dense than predicted. 2. It might stem from influences from ordinary matter. Disk shocking or feedback processes could suppress substructure or stabilize streams. 3. Maybe streams from recent mergers just haven't had enough time to be disrupted. But we see features that should have been deformed if subhalo flybys were as frequent as CDM suggests. There's a key distinction too. When you view a stream from the outside, you can directly measure its curvature, thickness, and continuity, which lets you estimate the tidal field smoothness across larger volumes. For instance, if a stream bends gradually but stays straight, the host halo potential may be smooth, nearly spherical over that region. If the stream warps, folds, or kinks, that signals localized mass concentrations. Compare this to what we can do with the Milky Way. We get velocities, but geometry is reconstructed indirectly. With Andromeda, the opposite. Geometry is clear, but kinematics are sparse. Combining both perspectives is how we isolate the underlying gravitational physics. In other words, Milky Way streams tell us how stars move through a gravitational potential. Andromeda streams show us what gravitational potential does to those stars on a large scale. In the end, stellar streams are more than just astronomical features. They're precise records of gravitational history. They trace the architecture of our galaxy, stress test one of our most important modern models, and offer windows into the invisible matter that shapes everything. They're byproducts of galactic violence, dim rivers of stars, stretched across space, whispering tales of the galaxies the Milky Way has engulfed. We now live in a time where we can map the invisible through stellar streams, and we're only beginning to listen. But there's more to uncover, and we'll be diving into more of it. Subscribe if you want to know more about our tiny place in the universe.